Okay, this is a video on trigonometry and parallax. So I'll start with trigonometry. That started with the ancient Greeks around 500 BC with Pythagoras and the Pythagorean theorem. Trigonometry is the study of triangles, and this was further developed by the Arabs in this period from 600 AD to about 1000 AD, and then more developed by the Europeans in the Italian Renaissance and then through the rest of Europe. The ideas here are important for science and for engineering and for astronomy. Astronomy is important, of course, for navigation early on and for understanding the motions of the planets, for astrology, motions of the sun and the period of the year in order to determine the days of Easter and for an accurate calendar. And there were important relationships between the angles of a triangle and the sides of the triangle, and that's where it starts. So here we have the sine and the cosine and the tangent of an angle. So you see sine of theta first. Theta is a Greek symbol, and it's just a symbol to represent an angle. And the sine of the angle is always going to equal the opposite side, which is opposite to the angle. This side over here would be the opposite of theta, and it's equal to the opposite side divided by the length of the hypotenuse. Hypotenuse is another Greek word. It means actually stretched across, and so there you see the hypotenuse. Now only right triangles have a hypotenuse, though. The hypotenuse is always the side opposite the right angle. So you see the little square there means that that's a right angle, 90 degrees, and so this is a right triangle. And these formulas for sine and cosine and tangent are, the way they're written here, they're only true for right triangles. And these formulas were known by the ancient Greeks, and the names sine and cosine and tangent come from incorrect Latin translations during the Renaissance of an Arabic work that was originally based on the original Greek work. So it was a funny story about how the name sort of evolved into sine. Where did sine come from? It's from Latin for sinus, which was an error in translation of an Arabic word that the Latin translators thought was an Arabic word for a cove, but it was actually an Arabic word for a half chord, which is the original Greek word. So when you say cosine, you're just talking about the sine of the complementary angle, and tangent has a geometric significance that has to do with the tangent to a circle. And so these are the fundamental relationships between an angle and the sides of a triangle, and that was known all the way back to the ancient Greeks. And there's the law of sines. This is a formula that was actually discovered by the Arab mathematicians. Somewhere in the period from 800 to 1000 this really developed. The benefit with this formula is that it works for all triangles. So you see that I have the sine of A. What I mean is the sine of the angle at the point A. So the interior angle here, inside the triangle, that would be the angle A. The sine of that angle divided by the length of the side opposite will always equal to the sine of another angle divided by the opposite side, which would always also equal the angle at the third corner or third vertex divided by the length of the side opposite. Like, these are always going to equal. The angles could be different, the sides could be different, but almost magically, no matter what the angles are, no matter what the lengths are, for any triangle, it will always work out that if you take the sine of the angle divided by the length for each angle and each side, they'll always come out the same. That's pretty neat. And we can use that idea right there, those formulas, we can use for many practical applications. Let's take one here. Say you're looking at finding a distance to a point C off in the distance there. So if you can measure off a distance from one point A to one point B, and you know the distance between A and B, you can find a distance to a third point. This is what we mean by when we say triangulate, a triangulation. We're going to turn this into a triangle and use the law of sines to find the distances to that point C. So we might, for example, as a simple example, let's say looking at this, we take a sight from the point A to the point C, and we step down to the point B, and we also look at the sighting of the point C, and we look at the fact that the angles are different. Let's say that we measure the angles. We measure those angles to be 85 degrees at point A, and the angle at point B to be 80 degrees, right? So that comes from measuring the angle. We're not walking out to the distance, point C, we're just measuring the angle from A to C. Essentially the angle from the line A to B to the line A to C, right? And then standing at point B, we could measure the angle from the line B to C to the line A to B, right? So that angle is 80 degrees, that angle is 85 degrees. And then we know the distance between them, let's say that's given as 10 feet. So just that is enough to calculate the distance to point C. So let's say we want to get the distance from the point A to C. So if I want to do that, what I would do is say, well, if this is angle B down here, 80 degrees, then I will call this side the side B, because it's opposite the angle B. And if I have this as angle A, then opposite angle A, I'm going to call this side little a, and then I don't really need to give this a name. It's 10. It's given. Okay, and so in order to set up law of sines, I have to know all three angles, but it's enough that I know these two, and the fact that all of the angles of a triangle will always add up to 180. That's another thing that goes all the way back to the ancient Greeks, the knowledge that for any triangle, the sum of the interior angles is always 180. So if I've got 80 degrees here and 85 there, let's see, what does that add up to? 165, right? 80 plus 85 gives me 165. So if I know that the total is 180 and I subtract 165, what is that going to give me? That has to be a 7. That's 15 degrees. So I know this angle is 15 degrees. And now that I know all three interior angles, and I know this length over here, it'll be possible, I can now calculate this length over here, this side, little b, or I could calculate this side over here, little a. Either one. Why don't we go for the side b? Let's find the distance from A to C. So we use law of sines like this. We'll say the sine of 85, or sorry, how about 80, the sine of 80 over the side that I want would equal the sine of 15 over the side that I know. That's 15 degrees. That's 80 degrees. And if I want to know what B is, I'll use the 80 degrees because that's the angle opposite. So the sine of 80 degrees over the side B would have to equal the sine of 15 over 10. Now it's also equal to the sine of 85 over A. That's also true. What I could do is I write this one equation with only one variable, and so I can solve for that one variable. Right? When I want to solve for that variable, when I solve for that variable b, what I could do is just cross multiply the sine of 15 degrees times b equals 10 times the sine of 80. Now I'm going to use a calculator, of course, to figure out the sine of 15 and the sine of 80, and I'll do that in a minute. But if I have the sine of 15 degrees, which is a number that I can get on the calculator, times b, I'm just going to copy that again, sine of 80. The last thing now that I need to do is just get b by itself to solve this equation for b. So I'll just divide by the sine of 15. Whatever that number is, I'll figure it out later. And divide both sides by the same thing. Divide both sides by that one number, and that would cancel out. So finally I can say that b is 10 times the sine of 80 degrees. I don't really have to put the parentheses. It's understood to be multiplication when they're next to each other like that, divided by the sine of 15 degrees. All right, so let's get the calculator out and figure out what that is. Okay, so you see that I have 10 times the sine of 80 divided by the sine of 15, and those angles are measured in degrees. So I'm going to go to the calculator. Here I have a calculator, a TI-83, and you want to make sure that you're in degree mode. So I'm going to hit mode on this one and see it's actually in radian mode. So I'll move this down, change it to degree mode, and hit enter. And then I need to leave this menu, so I'll hit second and quit. Now I know it's in degree mode, so I need to remember what my calculation was. I'm looking at B is 10 times the sine of 80 divided by the sine of 15. So let's type in 10 and then times. You can say times, but actually it'll understand even if you didn't do the times. The sine right there, sine of 80, and then I want to divide that by the sine of 15, so hit sine 15. Okay, and then enter. I get 38. Okay, so the answer is about 38. What did I have? 38.05. 38, let's say 38.1 if we round it off. 38.1 feet. Okay, so that answers the question. How far is it from A to C? It's 38.1 feet. We could do a similar calculation. We could find the distance A from the point B to the point C, and then once we have these two sides, we could actually draw a right triangle in there if we wanted to. We could find the distance from perpendicular. Right? We could find basically the height of the triangle from this base if we wanted to know that as well. But that's the start. That's finding the distance to a point out there in the distance by just measuring angles. That's the beginning of the process of triangulation. Okay, so we've just calculated this distance from point A to point C, and that's pretty neat, but you might be thinking, so, you know, what is this really used for? And one of the first things that I thought of was sort of in a military application with finding a distance, a rangefinder. And so I found these pictures on the internet. Looks like something from the 1800s here, and then from the 1940s maybe there from World War II. And then I found this picture for a very modern rangefinder. You can see it's much better technology, obviously, and much smaller. And I wonder how, I don't know the accuracy of any of these. I didn't look that closely. Well, 550-yard range. This must be better, but obviously requires being much bigger. You notice that the two, binoculars are like two eyes on your head that can sort of sense a distance because you have that stereoscopic vision that you can, the range for your eyes, they sort of overlap, so you can sort of intuitively sense how far something is because you have two eyes. And so that's even already, in our nature how our brains work, the same kind of mathematics, and we're just using the logic of the geometry to get very accurate answers. So let's continue and try another example. Let's go back. Let's say you imagine a bigger distance. Imagine if it was 3,000 miles between the points A and B, somewhere 2 points on the Earth. Suppose that's the Earth, 2 points on the Earth, and let's figure out how far it is, say, to Venus. Okay, and you would be interested to do this because you could use that then to find the distances to all the planets and all the planets from the Sun. The Earth is 1 astronomical unit from the Sun. But until the 1700s, astronomers were not sure what that astronomical unit was in miles. They wouldn't know how many miles or kilometers it is exactly. They had good estimates for the Earth to Sun distance, but all they knew was from Kepler's law, which gave the relative distances of all the planets to each other, but we didn't know precisely at that time how far each one was from the sun. In the 1600s, Kepler showed that if you could find the distance between any two of the planets, you could extrapolate from that. You could find the distances for all of them to the sun. You can see a graph here of basing on observations of the period, knowing how long it takes to orbit the sun. For each one of them, you could then base the periods on you could determine the distance it is from the sun from the length it takes to go around if only you knew one of them, right? There's no way you could actually go out and take a tape measure and actually measure from the Earth to the sun. But if you knew that number, then you could actually say, based on that one, you could get all the other distances to all the other planets. Or even if we could just figure out the distance from the Earth to Venus. And that's the first really accurate scientific measurement that was done in the 1700s based on watching Venus go in front of the sun. And that's known as a transit. So as Venus moved across in front of the sun, like in this picture here, I've got Venus. This is obviously not at all to scale, but you can just sort of see that if you looked at Venus from two different points far apart on the Earth, then the position of Venus against the sun when it happens to go across in front of the sun, that would sort of allow you to measure the angle at those 2 points A and B on the Earth, and then from there you have the same situation as our previous diagram, and you could calculate the distance to Venus. And if you could calculate the distance to Venus, you could use that then to extrapolate the distance to the sun. And so that was done in the early 1700s. There's only about 2 transits of Venus every 100 or 150 years. It was in the early 1700s that the first good scientific estimates for these distances were finally made. So what we'll do is we'll go through this calculation. Imagine that you're at 2 different points. You can have observation groups at point A and another group at point B, and both of them make measurements of, let's say, exact point when Venus first begins to enter across the sun. So at that one instant in time when Venus is just starting to go across the sun, or you could also look at how long it takes, and based on how long it takes to go across the sun, and then it would be possible to come up with this angle here and this angle here. If you could measure these angles, we could get these angles here. So let's take an example. I just made up some numbers, right? And let's use these measurements at point A, 89.99 degrees to Venus, and at point B, 89.98 degrees to Venus. And from that, we'll find the distance from Earth to Venus by calculating this distance from A to V, just like we did before. Use the measurements that are given here. These are not really accurate measurements, and it's obviously not drawn to scale. I just made up the numbers so that it would give you a feeling of what that calculation would have been like when it was done first time in the 1700s. So to carry out this calculation here, I'm going to call this side B over there, and I'll call this side A here, and I need to find this angle. And I know this side here is 3,000 is already given. We know the distance between the 2 points on Earth. So let's see, if we have 89.99 degrees, let's take 89.99 and add 89.98. If I add those together, that's 17. That's 1819. That's 1819 again. And there's 1617. So 179.97 degrees when I add them up. So now what I need to do is take 180, because I know all 3 angles together are always 180. So 180.00, and I'm going to subtract off the 179.97, 0.9700. So that angle right there is 0.03 degrees. Find the distance b, just exactly as I did in the previous example. I'll use the law of sines. In this case, it'll be the sine of the 0.03 degrees, I know that's degrees, divided by the 3,000 distance, would be equal to another fraction, which you could use either one of these angles. And since I'm looking for b, just as before, I'll use this one here. So it'll be the sine of one angle across divided by the opposite side. So sine of 0.03 degrees over 3,000 equals the sine of 89.98. This is true for any triangle, so it'll be that angle divided by b, which is the side that we don't know. And so now I want to solve for b. So let's cross multiply again. B times the sine of 0.03 degrees equals 3,000 times the sine of 89.98. Of course, if I want to get b by itself, then I'll divide both sides by this factor, sine of 0.03, which I don't know what that is. Of course, I'll use a calculator. Sine of 0.03. And so when those cancel out, I have b by itself as being the number 3,000 times the sine of 89.98, all divided by the sine of 0.03. So we'll go to the calculator and try that out. Okay, so the calculation that I'm trying to do now is 3,000 times the sine of 89.98, and then I'm going to divide that by the sine of 0.03. And I get, let's see, 5729577. Let's round that off. That looks like 3 places, so 5,729,000. 5 million. Now that's the answer based on the measurements that were given. But those measurements, I just made them up. The actual distance from Earth to Venus is something like around, what was it? Something like, I think 23 million miles when it's the closest, when it's on this, on the same side as the Earth from the Sun. It could go much further away too when it's on the opposite side of the Sun. But so this is not at all accurate. It was just an example I made up just to give you a feeling of what the calculation would be like. So the angles would be, the difference in the angles is even smaller than what you saw here in order to determine that huge distance. Okay, so that was the answer to that question. Okay, so we just found the distance from point A to point V. We find the distance from Earth to Venus by calculating the distance from A to V. And we use the measurements that were given. They are not accurate, they're not to scale, but based on what we're given here, we come up with an answer of 5,729,578 miles. And that's very similar to the principle of parallax. I mean, that is the principle of parallax, very similar to the calculations that were done in the early 1700s with the transit of Venus. As it crossed in front of the Sun, mathematicians and scientists and astronomers were able to determine how far Venus was from the Earth. And once they knew how far it was from Earth to Venus, they used Kepler's laws and they could figure out how far it is from Earth to the Sun and from every planet to the Sun. And so it was a better understanding of the solar system. And so let's move from that now, understanding how far it is from the Earth to the Sun. Let's go on a even bigger scale. Let's say from point A to point B in this same kind of diagram, but let's take those 2 points, A and B. Imagine they were 186 million miles apart. I get that number from thinking 93 million twice, right? The distance from the Earth to the Sun is about 93 million miles. So if I put 93 million miles between the Earth and the Sun, here, 93 million miles, and then it stays approximately 93 million miles all year long. The only reason for the change in the seasons is not because the distance changes. It does change a little bit, but the reason for the change in the seasons is because of the tilt of the Earth. And so here in March, the Earth is tilted not away, not toward, but just sort of in another direction, so that the season, the length of the day is the same for everybody here in March. And then in summer, maybe it's over here, and the Earth might be, if you're in the northern hemisphere, would be tilted toward the sun. And then later in September, it's not pointed toward, it's not pointed away. You're back in the same orientation as in March, 6 months later. So half a year to go around the sun. And if we take a radius of about 93 million miles for that circle, then we get a total diameter here of the circle of 93 million times 2. 93 million times 286 million. And that's the distance of my base here in this triangle. So now we're going to use that distance and look at a nearby star at different times in the year and see if we can figure out how far the star is from the sun. So let's look now if there was a star that was nearby so that its position changed during the year relative to the other stars. If you notice during a year that one star moves a little bit against the other stars, that's using the principle of parallax. Parallax would be the different orientation depending on your vantage point, the different orientation, sort of the apparent motion there of that object when you're looking at from one direction versus another. I forgot to mention how you could observe parallax yourself. Just hold out your hand and look at your thumb and close one eye. When you look at an object, your eyes will, because there's a little bit of distance between them, will see your thumb at a slightly different angle, and that's how you're able to sort of give a sense of distance just intuitively by the parallax effect of the two eyes that you have on your head being just a little bit apart. So we're using that same principle of parallax here and looking at really far distances. Imagine you've got two eyes, one eye in March and one eye in September as the Earth spins around the sun, and we're looking at, instead of a thumb, we're looking at this nearby star against the background stars. And so over the year, that star would appear to kind of move from one, between, in March, the star here at point C seems to be between these two stars, and then later in September, it seems to be between these two stars. So it seems to have moved against stars that are farther away. So we can get our first step toward calculating the distance to the stars by parallax. It doesn't move very much, and so you've got to have really accurate measurements of the angles. And so let's try. Let's say if we could figure out what those angles were, we could determine the distance to the star. Since we now know the distance from the Earth to the Sun, we could actually calculate this base distance and create this giant triangle in space and determine the distance. We can triangulate to the nearby star. So let's take this example here. Let's draw the picture this way. I want to calculate the distance from the Sun to a nearby star based on some given angles. So let's say, suppose that the star moves a distance of 10 degrees through the sky from March until September. And based on that one angle right there, how do we calculate, knowing the angle and knowing this distance, that the Earth has traveled around the Sun. See if we can calculate the distance to the star. So find the distance from the Sun to the nearby star at the point C, and let's use the measurements that are given here, which aren't really accurate and they're not to scale at all, and see what we come up with. So what I'll do is I'll say, well, if you wait exactly 6 months, then these two angles will be the same here, and then we can create this isosceles triangle. We can take that 10 degrees and just split it up into two angles of 5 degrees each. And with that calculation now, what I'll do is say this distance x is the distance I want to find. Okay, so you see I'm trying to find that distance right there, x, from the Sun to the nearby star, and I've measured a parallax angle of 10 degrees. That's given in the question. And so if these two observations are taken exactly 6 months apart, then the Sun would be right in the middle here in this diagram, and so these two angles would be 5 degrees each. We know the distance from the Sun to the Earth is about 93 million miles, and now we can get a very good accurate estimate for the distance to a nearby star. So finding that distance x, let me emphasize again, it's this distance x that I'm trying to find. Okay, so if that's the given information, let's figure out what is the distance from the Sun to the nearby star. Well, what I'll do is I'll use a right triangle. I'll take this to be 90 degrees. This right here is a right triangle. And in that right triangle, I can use, all the way back from the beginning of the video, remember we had tangent of an angle is the opposite side, the length of the opposite side divided by the length of the adjacent side. And so that's all we need to do here. It's actually easier. If we know that angle is 5 degrees, we can say that the tangent of 5 degrees equals the opposite side. Opposite to 5 degrees would have to be the 93 million. So that's 93 million divided by the adjacent side, which of course is the question that we're trying to figure out. So if we have all the other information, the angles here, and we know the 93 million miles from the Earth to the Sun, we can find x. So how do we solve for x? You could just cross multiply again. Let's say that's over 1, right? If you want to look at it like two fractions, then cross multiply, you get x times the tangent of 5 degrees would equal 93 million. And so solving for x, I want to divide both sides by the tangent of 5 degrees. So those would cancel out. X is 93 million divided by the tangent of 5. Now, you can use a calculator, of course, to get the tangent of 5 degrees. So let's do that. I'm typing in 93 million. I need 6 zeros, and then I'll divide that by the tangent of 5 degrees. Make sure you're still in degree mode, so that's the tangent of 5. And it looks like, well, that's three places, that's 1,062,994,864 miles, so a little over 1 trillion miles based on those measurements. Okay, so there's my answer, 93 million divided by tangent of 5 degrees. I've got 1,062,994,864 miles based on these measurements. They're not realistic. Actually, the nearest star is around 23 trillion. This is about 1 trillion, really 23 trillion miles to the nearest star. But this gives you a sense of how the calculations are actually done. And this, of course, only works for nearby stars. Stars that are even further needed another technique besides parallax to determine their distance. Okay, so just to finally wrap up here, I thought I'd point out on this last calculation, the reason I did with this calculation with tangent, and it did seem easier here at the end, was because it just worked out that the information that was given, we had a right triangle, and the tangent, as I used it here, would only work for a right triangle, opposite over adjacent in a right triangle. And the reason I had a right triangle is because I gave these two measurements, these two sightings, 6 months apart, and so because of the angle 10 degrees in the apparent motion of that nearby star, because that was 10 degrees, that would be the biggest that angle would be. That would be the biggest that the nearby star would travel in degrees across the sky, and therefore if you split that in half you could create a right triangle. And so with the right triangle, you can see right there is the right triangle. 93 million miles over here from the Earth to the Sun, and an angle of 5 degrees. I use the tangent of that angle as the opposite side over the adjacent side. So the tangent of 5 degrees is 93 million divided by x, and then we multiply both sides by x, or cross multiplied, and then we divide it by tangent 5 degrees, and we divide it by tangent 5 degrees. It gave me the answer. So that worked in that last one only because we had a right triangle here. And now if you think back, wow, what were we doing before, and maybe in one of those earlier examples, let's go back maybe all the way back to that first one. Here I didn't have a right triangle right away because I had these two angles, 85 degrees and 80 degrees, weren't the same. We're not directly given a right triangle. We could have created one in here, but in order to create a right triangle, we would have had to find a horizontal here perpendicular 90 degrees to the side AB, and we'd have to do this first actually to get a right triangle. So this was a little bit more involved. It required the law of sines, right? So just to wrap up again, the law of sines was this rule that says the sine of any angle over a side opposite would always be equal for all of the angles and all of the sides in any triangle. And then only specifically for right triangles, like here, I could use the relationship, the very beginning relationships in trigonometry, sine, cosine, and tangent. And I never actually used cosine in any of these examples in this video. But we used tangent at the very end where we had a right triangle. We did the tangent of an angle is the opposite side divided by the adjacent side. And so I'll also point out how you may need to do some experimenting with your calculator if you don't have the same one I had there. This one isn't interactive, but I've got a button here that'll change it between degree mode and radian mode. So you don't want to do these in radians because the angles that were given here were all degrees. So make sure you're in degree mode and look for the button for sine and for tangent, and you ought to be able to get this to work out. There's another thing you could do. Another thing that you could do just to, since you've got the computer, of course you might even have the calculator already in the computer, and you could try a website like Wolfram Alpha that's free, and you could see wolframalpha.com, www.wolframalpha.com, and you could do something like sine 85. Now this thing is smart enough that if you just type sine 85, it'll give me that angle it'll interpret it in degrees. We could change it to radians. It'll tell me sine of 85, and there's my answer in decimal. 0.99619, and it's really accurate, right? So you could do some checking, make sure your calculator, you understand how it works. You could use this thing to play with. This is something that could possibly come up on the exam, so you want to have at least a scientific calculator. These are the TI-30 and TI-36, something like this should be around $10, maybe $15 at the most. And that's all you would need. You certainly don't need a graphing calculator for the exams in this course. All right, so that is the end of the video. I hope it was helpful and interesting.